Okay, in this video we're going to have some fun setting up the Kinetis TouchSense input module. So this allows us to use touch inputs like your phone. It's a capacitive touch sensor design, and the microcontroller itself has a hardware module in the microcontroller, so you can pretty much lay out a touchpad on your printed circuit board, like on the K65 board, or on a screen or anything like that, and basically do touch sensing. Here are all the references. Of course, the main reference, which I hope you're getting familiar with, is the reference manual. It's chapter 64 that we need for the touch sensor. The touch sensor also has some electrical specs because it has some characteristics that we have to deal with when we're interfacing this with an electrode or a basically touchpad. So that's in the electrical specifications of the data sheet. Then we have a couple application notes. This touch sensing software using the TSI module, well, it's kind of interesting and what you could do with a TouchSense module, and especially how to debug. It has a system where you can watch the touch counts and stuff, which is very interesting, especially if you're developing a TouchSense system for a product. You're going to be doing a lot of experimentation. So this kind of leads you through that process. I think the most interesting is probably this one here on designing touch sensing electrodes. It kind of explains how capacitive touch sensing works and how you would design different kinds of electrodes. And then on our board schematic, that shows us where the two touch sense pads are connected. And then the peripheral access layer allows us to use the macros related to the touch sense module. And then I also have a demonstration program for touch sensing that's set up for the K65 touch sensors. That can be really useful. Basically is set up for you already. It's designed around a time slice scheduler, so it's ready to go. Okay, touch sensing. Well, as you all know, touch sensing has really taken off. You use it on your phone, but also many other products. The old classic capacitive touch sensing was the lamp that you would. I remember my uncle had one a long time ago, and everyone was just amazed that you touched the lamp and it turns on. That's kind of the earliest example of touch sensing. Now my car, I touch the door handle and it unlocks if I have a key in my pocket. So lots of different examples of touch sensing out there. And of course, the big advantage is that there's no mechanical wear. We saw the switches are these mechanical contacts, and they bounce when you push the button, and they slowly wear out. They can also be transparent, like on your phone, where you just touch. It's some kind of software icon that it corresponds to a button. They're weather and contamination proof. Now, that is that, you don't get the weather, the rain or whatever getting into your circuit because a mechanical switch, it's difficult to seal that off. A TouchSense pad, it's no problem to seal that off. There's no gaps or holes or anything like that going inside the circuit. Now, the weather certainly can affect your touch sensing, which I'm sure you've all experienced when you have a wet screen and it doesn't quite respond the way you want on your phone. Disadvantages, yeah, that's one of them. The impedance, or the capacitance of the touchpad changes with different environmental characteristics. The other interesting disadvantage is one that is a kind of a hot topic now, and that's haptic feedback. Haptic feedback is the mechanical feel. So when you push a button, if it has really good haptic feedback, you feel the click of, when the button makes contact. Keyboards are really good with that, and a poor keyboard is going to have very poor haptic feedback, which then doesn't give you feedback that you actually press the key. So when you're, it's like pressing, using the keypad on your iPhone or iPad or whatever. It's a little different experience typing on that rather than a real keypad. So they're working on different ways of creating haptic feedback when it's really important. Things like musical instruments or something like that would really need that good haptic feedback. Okay, so this is going to be how the module works. We have the start of a conversion, the end of a conversion. So this is called the touchpad scan. So we're scanning the touchpad to see if it's been touched or not. The way it works is we have two oscillators. We have the electrode oscillator that's controlled by the touchpad itself, the capacitance of the touchpad. And then we have a reference oscillator that's frequency is controlled by the internal oscillator. So what happens is that while we are going through these counts, we're going through these cycles of the electrode oscillator. While we're doing that, the circuit is counting the number of cycles in the reference oscillator. All right? So when we press the touchpad, the capacitance goes up. And what the effect that has is that the frequency of the electrode oscillator goes down. So you can see if the frequency of this goes down, we're going to have more of these cycles in one of these scans. Okay? So that means that the count will go up as we get our finger closer to the touchpad. And that count is how we know if it was touched or not. So this is the equation for the count. It's the reference frequency over the electrode frequency times this prescale value and the number of scans. These two parameters are configurable, and they allow you to adjust the resolution and range of our count. Okay, you can see if the frequency of the electrode goes down, then our count goes up, just like I just explained. Here's the calculation of the frequencies, and this is a basic capacitor-based oscillator. And so what happens is we have a current, this Iref in this case, that's charging a capacitor, making this slope, right? We have a current going into a capacitor, and the voltage goes up or down. And so that frequency is based on the current, on the capacitance, and then the delta V are the two thresholds that are detected to turn the cycle around. So if we reach one threshold down here, we start going up. We reach the other threshold, we start going down. We reach the first threshold, we go up. And so this delta V here is basically the difference in voltage. So you can see as your delta V is smaller, then the frequency goes up because you don't have to go as far. If the capacitor gets smaller, the frequency goes up. If the current is smaller, the frequency goes down. So it's all about this current, this capacitance, and this delta V, and all three of these parameters are configurable in our TouchSense module. So it's the same with the electrode. This is the reference, so it has this reference capacitor and this reference current. And then we have here the electrode one. This is the one that's going to change because it changes with this capacitance, which is the capacitance of the touch. So in the notes, I describe what values I have set for these. And this was all done experimentally with the K65. I just sat there and looked at counts and the touch pads and just, tried to find the reasonable value for these parameters. What I did first was set up this reference so that it was at the highest frequency that was usable. And the reason for that is because it allows to have a really high frequency here. We're going to have a lot of counts in here, which means that we don't have to scan as long to get the full count. So by setting this reference frequency to as a large value, it decreases the time it takes to scan the touchpad. Now, it all depends on the capacitance of our touchpad. We may not be able to do that with a different touch sensor. All right, so then I also go over in the notes on how we set the current, and the electrode capacitance is based on whether you're touching or not, and the delta V. And so from that, with no touch, I get a count of around 14,322. Okay, in decimal. So that's the number of counts. That's the number of these cycles here that there were in one scan without touching the touch sensor. This is what we might call our baseline. Okay, I'll talk about that more later on. Now remember that our range is 0 to 65,536 because the count is a 16-bit value. Okay, so we're down on the lower end, which makes sense because when we touch, this count's going to go up because the frequency of the electrode goes down when we touch. So this count's going to go up. So we're going to start at 14,000, and as we touch, it's going to go up to a higher count. The reason that we don't start at 0 is because there's a lot of variation based on the environment and the layout of the board and all of that, and we certainly don't want this to be stuck down at 0, all right? So this gives us a little room between 0 and the baseline. Okay, so we know that we are going to start a scan. We're going to scan a touchpad electrode. Those two oscillators are going to go. After the certain number of cycles of the electrode oscillator, we're going to stop and we're going to capture that count, and that count's going to give us an idea whether the touchpad was touched or not. Now, the scanning happens periodically. Think of a keypad, right? Where we're periodically scanning the keypad to see if a key was pressed. It's the same situation with the touchpad, where we're scanning the touchpad to see if one of the electrodes was touched. Now, how long does it take to scan? We have this value here. This is the length of time it takes to scan the touchpad, and it's equal to the prescale value times the number of scans divided by the frequency of the electrode. Well, so let's look at an idea. I tried to, as I said earlier, I tried to set the frequency of the reference as high as possible so we could lower the scan time. Well, with that setting, I'm getting about 4 milliseconds per scan when it's touched. Okay, and so this is a touch time, which is the worst case, right? The time it takes to scan, because the electrode frequency goes down. The electrode frequency goes down when you touch it, so the time it takes to scan goes up. So the time it takes to scan the touch sensor depends on whether you're touching it or not. And so this is kind of the worst case. It's 4 milliseconds. It's kind of the worst case, and it's when we're touching the electrode. Well, 4 milliseconds, when we think about our time slice scheduler, 4 milliseconds is a significant amount of time, right? It's, if we had a time slice period of 10 milliseconds, well, that's 40% of our CPU load right there. So we need to be a little tricky on how we deal with this, and there's a few ways to deal with it. I'll show you one way to deal with it with a time slice scheduler, and then there's also, we could do this with an interrupt-based system as well. Okay, as I mentioned before, the capacitance of the electrode depends on the environment, temperature, moisture, the layout of the board, all kinds of things. And so the count is going to vary depending on the conditions. So in that case, what we need to do is perform a calibration, okay? And so what we do, the normal initialization, like we would with any other module. We initialize it, we enable it, stuff like that. And then the first thing we do when we come out is we do this calibration. And this is the name of the calibration in our TouchSensingTSI demo program. And so let's go over this code a little bit. The argument is the channel. The K65 has a possibility of 16 channels, and those channels are numbered from 0 to 15. So this argument is a number from 0 to 15. Turns out that the two electrodes on the board are connected to channel 11 and channel 12. So electrode 2 is connected to channel 11, electrode 1 is connected to channel 12. So we'll be using channel 11 and channel 12 for this. Okay, so each electrode has its own channel. And then when we get into this calibration function, the first thing we do is we start a scan. And we'll look at this function in a little bit. And so we're starting a scan for the channel number that we just passed into the function. So now it's scanning. And so what we have to do is wait for this EOS flag, that's the end of scan flag, to be set. And that indicates that we are done with our scan. So that is between the start of this scan and this flag being set, that's that 4 milliseconds that I was just talking about. That's how long it takes to scan. So here we're just waiting, we're in a while loop. And while this flag is 0, we just do nothing. So we're stuck in this loop until this flag is set. Once the flag is set, we need to clear the flag by writing a 1 to it. And then we're going to take the readings from the scan. And the count from the scan is in the TSI 0 data register. But it's the TSI data, TSI count mask. It's 16 bits in that register. So we have to AND the contents of this data register with the mask for the count. And then we say that's the baseline. All right, so I have a structure here that are the TSI sensor levels, and there's one for each channel. And so we have 16 of these. And so one of the members in that structure is the baseline, and that's what we just read from this calibration is the baseline. And so it's going to look like this. We have, say, a count of 0 all the way up to account, I'll do hex so it's easier to write, of all f's. All right, so that's the range of our count. And now we're going to have a baseline. So this is our baseline. And then we're going to have a threshold. Okay. And so if the count is below this threshold, so if the count is below this threshold, then the system will say it's not touched. If it's above the threshold, it is touched. So now how do we get the threshold? We use this baseline, which we just found here, right? We found the baseline right here, which is in the calibration, and it's the data from the calibration. So we did a scan, and of course this calibration cannot happen if you're touching the sensor, right? This calibration has to happen when we're not touching the sensor. So this will be the non-touch, that's the baseline, that's the no-touch baseline value. And then the threshold value we calculate by taking the baseline and adding an offset. This offset in my demo code is a constant, and it often is. I can imagine a system that changes dynamically, and I'm sure things like your iPhone change dynamically as it looks at the weather and the response to the touchpad and stuff like that. And so in that case, the offset might be a variable. So that's why I put it as a member in the structure, even though we're just looking at this offset as a constant. And what I did is I experimented with several touches and set an offset. So the offset is basically this difference between the baseline and the threshold. All right? So when we do the calibration, we acquire the baseline. Then we have an offset, and based on this baseline and the offset, we have the threshold. Okay? So if the baseline moves up, the threshold moves up. If the baseline moves down, the threshold moves down. So that allows us to calibrate the touch sensor. So what we're always going to be doing is running initialization, and then we run this calibration one time. I can imagine you could set up a system where you're running this calibration more than once, and you can make the calibration a little smarter by looking at the actual value and seeing, well, that's, if say the count is up here, you could say, well, wait a minute, the count is above the threshold. It looks like someone's touching the sensor, so let's not do a calibration now. If the count's down here in the baseline, it can say, okay, this is a good time to do a calibration, and then maybe it changes this baseline a little bit. The first thing we need to do is start a scan, and there's several ways to do that. We can do it with a hardware trigger, or we can do it with a software trigger. In this example, the TSI demo example, I use a software trigger only. It's simpler. With the software trigger, what it allows us to do is start a scan in our time slice scheduler so that we have a periodic scan. And that's fine because how often you need to start a scan is on the tens of milliseconds scale. It's not anything faster where we have to do some kind of hardware. But we could certainly set up a pit timer to trigger. If we had it set to a hardware trigger, we could set up a pit timer to trigger the TSI sensor to start a scan at some periodic rate based on the pit timer. Bottom line is that you cannot have that scanning period be smaller than the time it takes to scan. because what will happen if you make that scanning period smaller, then we end up with an interrupted scan and we don't get any scan results. Okay, so the scanning period has to be greater than the time it takes to scan, which for our demo program we saw was about 4 milliseconds. All right, so here is the TSI start scan. And again, the argument is the channel. So we'll be looking at channels 11 and 12. And so this first, in the data register, this data TSI channel, you pass it the channel. And so that sets the data register so it knows what channel it's scanning for this start of scan. Okay, so we've set the channel here. And then we start a scan sequence by triggering the software trigger. Okay, so this software trigger, we write a 1 to it. Again, it's in the data register. We write a 1 to it, and it will start a scan in this channel. Okay, so we have to do this start scan for each channel. All right, we can't do all of them at once. So again, we pass that channel into the argument, we set the channel, and we start a scan. Okay? So that's the start scan sequence. All right, now the process scan. So this is what we're going to do when the scan is finished. Again, it's the channel as the argument. And so the first thing we need to do is wait for that EOS flag. So again, like the calibration, this is the same process as the calibration, except we do different things with the results, where we have to wait for that end of scan flag to know that we're done with the scan. And so we're just waiting for it to be non-zero. We're stuck in this while loop. And then when the flag is set, we clear it by writing a 1 to it. Okay, so this time, instead of setting the baseline like we did in the calibration, this time we're going to take the data. So this is the data ANDed with the count mask. So this is just the count, and it's a 16-bit unsigned integer. If that is greater than our threshold, so if the count is greater than the threshold, then we say that the sensor was touched. And so I have a variable here called TSI sensor flags, and there's a bit for each sensor. So this is a 16-bit variable. So there's 16 bits, and so we take a 1, shift it over by the channel. So let's say it's 11. We shift it over 11 times, and then OR that, so that sets bit 11 of the sensor flags. If the threshold wasn't exceeded, if this value was smaller than the threshold, then what we do is clear bit 11 or whatever the channel bit is. And we do that by inverting our 1 in channel, so that makes everything but bit 11 1. And then we AND that, so that clears bit 11. All right, so that's how we process the scan. If the sensor was touched, we set bit 11 or the channel bit of this flag variable. If it was not touched, then we clear the bit of that flag variable. So that's the processing. Okay, so here I want to go over, this part isn't in the notes, it's in the TSI demo. Now we saw that the scan time was 4 milliseconds. So if we did the start and the process scan in the same time slice, then we would be stuck in that task for 4 milliseconds. So if our time slice scheduler was set at 10 milliseconds, then all of a sudden 40% of the time is just waiting for a key to be pressed. So that's why I separated the start of scan from the processing of the scan. It seems kind of strange that we would take those 2 lines in the start of the scan and separate those 2 lines from the processing of the scan. But the reason is that I want to alternate the processing and starting between different states of our task. So here's an example of a TSI task, and we have a state variable called TSI task state, and there's two states. There's process 1 and start 2. And so basically this is a state where we're going to process the sensor 1 and we're going to start sensor 2. And then we have the process 2 start 1 where we're processing sensor 2 and starting scan 1. Okay? So the first thing I have to do just to initialize this, I have to start a scan, and I start a scan on the board pad 1 channel. So this board pad 1 is the label in the schematic of the pad 1 sensor. And it's a channel, so we're passing that channel. So this is just a define. Turn on a debug bit. This is allows me to check to see how long it's taking to do this. And then we have a state machine here based on the task state. Okay, if we started in the process 1 start 2, then we process the scan. So you'll notice that we started the scan here for pad 1. Now we're processing the scan for pad 1. We start the scan, or we process the scan on pad 1, and then we start the scan on pad 2, and then we change the state to process 2 start 1. All right, then we leave. So then we go into process 2 start 1, we process the scan of pad 2, and we start the scan of pad 1, and then we change to process 1 start 2. So basically what's happening here is that we're processing the scan that was started in the previous time slice, and then we're starting a scan for the next time slice. Okay? So we're not waiting for that flag. We're not blocking, waiting for that end of scan flag. We're going to look at it when we get back into this task. And that works really well, because if we set this task to the right task period, then what happens is that the flag is already set because the scan is already done by the time you get back. And we can look at that in this sequence time diagram here. Okay, let's say we have the task, and we have the TSI. Okay, and let's show our time slice. Okay, so here's our time slice, and so it's getting into the task on each one of these. Each one of these is the time slice event. So that's when it gets into the task. If we did this in the traditional way, where we just start a scan and wait for the flag, so we're going to send a message to the TSI, and that's the start scan. Now, this, by the way, this is time in this direction. This is really exaggerated. I mean, the start of the scan is 2 lines. That's a very, very, very small amount of time. But it's impossible to draw this to scale, so I'm just showing it like this. So in the traditional way, it would then be doing the TSI would then be doing the scan, and then the EOSF, the end of scan flag, would be set, and this process task would go back. I made this really bad. There's the process task, and then we'd finish the process and we'd be done here. So you can see out of our time slice, all of this is used by the TSI, and all we have left is this. So that's pretty bad, right? In our example that we were just talking about, this part would be 4 milliseconds, and these time slice periods would be 10 milliseconds. So it's showing a little extreme there. Okay, and then we would just do this over again. Start, and then we would do a scan, and then we would finish it, and we would process it, and we'd be done again here. Okay, so you can see we're using up almost all of the time slice waiting for this end of scan flag. If we use the method that we just showed up here in this task, here's our task, here's our TSI, okay, here's our time slices, okay, and so what happens is that the task sends a start to the TSI, okay, and the TSI starts doing a scan, and the end of scan flag gets set there, right? Same as the other side. The difference is that the task sends a start and then it leaves, okay? And this is the first one, so I skipped the processing part. So it leaves, and then the next task, what it does is it calls the process, and when the process, when you call the process, the end of scan flag is already set, so you're not stuck in that loop at all. You immediately go through it, and then you process it, and then you send a start, okay, and then you leave. Okay, so now, let's see, the amount of time that we're spending is this and this, right? And the amount of time we have left is all of this. So our CPU load just went way down as far as the time slice scheduler goes. And so while this code looks a little complicated for what it needs to be, what it does is it allows us to do other things in this area in here. We can do other things instead of just waiting for that end of scan flag like we do here. Okay, now the overall delay between the time we start a scan and process this and get the value of the scan, here the delay is from here to here, and so that's smaller than our time slice. Here the delay is from here all the way down to here, so you can see it's longer than a time slice. But that delay is usually not the issue, all right? The delay, if we're talking about doing this every 5 milliseconds or something like that, it is certainly okay to have a 5 millisecond delay from the time you push the touch sensor. That's much better than our keypad, by the way. So that stopwatch, we could make a better stopwatch if we used a touch sensor. Okay, so that's why this TSI task is designed like this. And that's an example of using the Kinetis TSI touch sensor module.